Good evening, everyone. My name is Bhanuka Mahanama. Today, I'm going to present our paper titled Multi-Eyes, a framework for multi-user eye tracking using web cameras. So let me start with the question, what is eye tracking or gaze estimation? We can simply define it as approximating the gaze location of a person. We can express it as the gaze point of gaze or the gaze direction of the person. Eye tracking or gaze estimation has wide variety of applications. Some of them include human-computer interaction, psychology, and market research. There are two approaches to do the gaze estimation. The first is to use eye trackers, a dedicated and specialized hardware and software combination designed for estimating the gaze direction. The second approach is to use the commodity hardware or web cameras to estimate the gaze location. Here, the camera captures our facial images and estimates the gaze based on the features. So this brings us to multi-user eye tracking. Multi-user eye tracking can be simply defined as performing eye tracking in a multi-user environment. In addition to capturing individual user behaviors, in a multi-user eye tracking, we can capture collaborative behaviors such as joint attention and joint mental effort. But the problem is this requires us to capture the gaze of all the users in the environment, which brings us to the challenges. The first challenge or the main challenge is that the eye trackers or the specialized hardware and software can capture the gaze of only one user. Therefore, in a multi-user environment, we need to have a dedicated device for each user, and depending on the cost of the device, the overall setup can be very costly. In addition to that, it will make the setups more complex and also highly constrained to avoid the interference between these eye trackers. So there's one way to overcome this problem or the challenge. That is to use the commodity hardware such as web camera for multi-user eye tracking. Here, the web camera will capture the facial images of the users in the environment and performs the gaze estimation. Considering the recent advancements in computer vision and gaze estimation techniques, this approach provides a promising solution for our challenges. For multi-user eye tracking with commodity hardware, we propose our framework called multi-eyes. The architecture of our approach has three main steps, starting with user detection, followed by gaze estimation, and finally mapping the gaze into real-world objects or targets. Now let us go through each of these steps in detail. The first step of the pipeline is to perform user detection or identify the users in the environment. In our prototype, for the simplicity, we consider the scenario of two users in two designated regions as left as right. Also, for the simplicity, we assume there are to be no occlusions or movement of these two users. Then we use face mesh to detect the faces and establish the boundary boxes. Then after that, we crop these images and resize each facial image for the next step of gaze estimation. In the next step of gaze estimation, we use the images from the previous step and estimate the gaze directions. Here we use a convolutional neural network or a CNN that takes the facial images and estimate the gaze directions in terms of pitch and view angles. For the CNN, we use a efficient net architecture-based CNN and start with the ImageNet pre-trained weights. Then we fine-tune the model using XGS dataset for another 50 epochs and with a 80-20 training and a validation split. When developing the gaze model for the application, we consider the idea that each facial image to have two types of features, as gaze-defining features and non-defining features. We extend the same idea into the latent representation or latent spaces and model the relationship using a modified autoencoder. In our model, an encoder forms a latent representation E. The latent representation E, then we split the latent features between two categories. Gaze-defining features as EG and non-defining features as EF. and EG or the gaze defining features having a dimensionality of 2. Then we use two decoders in the next step. The first, uh, the first, uh, the first uses all the features and reconstruct the image, and the second one uses the gaze defining features and estimates the gaze deviations. Due to this, our loss function has two terms, LG from the gaze loss and LR from the reconstruction loss. We combine these two terms using a hyperparameter lambda R and form the final loss function or the loss of L. Depending on different combinations of lambda R and K, we can derive different forms of gaze estimator models with different characteristics. Now, this brings to the last or the final step of the pipeline, which is the gaze mapping, where we map the gaze directions into real-world objects or targets. Since we use a screen as the interaction interface, we map the gaze directions into on-screen coordinates. As the first step, we need to estimate the location of the users in the 3D space. For estimating the location, we use an image projection and form a grid-like and form a grid based on the location of the face in the image. We use these encoded, we call them as the encoded face portions, and we use these encoded face portions and then combine with the gaze directions to estimate the on-screen gaze locations. Here we assume a nonlinear relationship between the inputs that are, which is against the angles and the encoded face portions, and model it with the multi-layer face approach. We train this small model during the calibration phase of our multi-user eye tracker. Finally, we use these on-screen gaze locations for analyzing the user behaviors. So this brings us to the results of our study. Our first analysis was on the gaze estimation capabilities of our model. For our studies, we used a latent space with 64 dimensions with no reconstruction regularization. First, we tested the model with XGS dataset. We first trained the model with XGS dataset, and our model achieved a comparable results while using a fraction of parameters used by the baseline. Also, we observed bigger models to yield better results, indicating possible improvements. Considering the two hyperparameters, this indicates potential for more optimized models beyond the scope of our study. In our next investigation, we investigated the effects of hyperparameters K and lambda R using the efficient net zero-based model. Our investigations did not find any clear relationship between the hyperparameters and the overall performance of the model. We also investigated the effects of quantization, which allows where we execute the model with low precision by discretization, allowing us to lower the computational load while compressing the model. In our study, we observed mixed results for the quantization and the performance. In the next evaluation, we investigated the cross dataset performance of our gaze estimation model using the Columbia gaze dataset. The dataset has around 5,800 images with over 50 participants. We did not observe any clear relationship with the model configurations, but we saw the worst error of 7 degrees and a best error of 5 degrees for the gaze estimation. These results indicated better generalizability in the model compared to literature and provides a potential baseline for investigating the generalizability in future research. We also expect calibration and model scaling as possible ways to further improve the model performance. In the next study, we recreated a joint attention experiment using our prototype. We recruited 5 participants and conducted 3 trials with the proctor instructing the participants to stare at on-screen target. During each session, we collected gaze portions and computed fixational gaze measures, including fixation duration, count, and the time to first fixation. During the experiment, we observed comparable results to literature indicating the feasibility of our prototype. In our final investigation, we evaluated the throughput of our overall setup by analyzing the performance of, or the throughput of our setup during the joint attention experiment. We observed an average throughput of 17 gas samples per second with a maximum of 20. Considering our setup having no hardware acceleration, this indicates a possible area of improvement. In summary, we introduced multi-eyes, a framework for multi-use eye tracking using web cameras. And in our study, we identified a set of lightweight parameter efficient gas estimation models, which also offers the scalability. We also demonstrated the feasibility by recreating a joint attention experiment from the literature. And using the same joint attention experiment, we demonstrated the utility of the overall framework and also the gas estimation models. And also our setup provides approximate locations and with a low sampling rate. As future directions, we expect to experiment on the module configurations and possible hardware acceleration and end-to-end evaluation of our framework. And that is the end of my presentation. You can reach our research group through the Twitter and also through the email if you are interested in our study or interested in collaborating with our study. Thank you and have a great day.